Okay, the purpose of this activity is to help you with the chart of the Nuclides activity. So there are two problems with a couple parts. In each part, we want to write the complete decay series for each one of the radionuclides that you've been given. On the first problem, I want you to write the complete and balanced nuclear equation for each step in the decay series. For the second problem, these are a little bit longer, and so you don't have to write the complete nuclear equation for each step. You can just use a shorthand. Just tell me the type of decay and what the daughter is for each step. And I'll do an example of each one of these. So in order to do this, you need access to a chart of the nuclides. And so there's either a web-based version or there's an app that you can get for your smartphone. If you want to use the web-based version, just do a Google search for IAEA chart of the nuclides. And the first link that comes up should be this one, and this is the one that we want. And so here's the chart of the nuclides, and we can zoom in a bit if we want. Each one of these boxes is a different isotope of a given element. And you either hunt for it in the chart by navigating, or for example, if I wanted to know about uranium-235, I could type in 235U, and it gives me the information for uranium-235. The information that we really want from this chart of the nuclides is how it decays. And so if I go to decay modes, the top one is the most likely, and so I can see that it's basically 100% alpha decay. That being said, I think the app is actually easier to use, and so that's what I'm going to use for the rest of this example. So to get the app, you need to download it for your smartphone, and this exists for Android or iPhone. And so you need to go to the App Store and search for IAEA Isotope Browser. All right, and so when you find it in the App Store, it should look something like this. So I've already downloaded it, so I can go ahead and open it. And when you open it, you should see a home screen that looks something like this. And so we can type in the isotope that we're interested in this box here. And so for the examples, so this is an example of what we do on the front page, where we want to write the complete nuclear equation for this particular isotope. And so what I would do is in here, I would type in osmium or OS 180. So I'll look for OS. And if you notice, this thing is really bad about autocorrecting. So it changed my OS to IS. So I had to go back and change it. So OS 180, and then you can hit go. And so this gives us a list. Sometimes there's only one in the list, or sometimes there are metastable nuclides, but we want the top one. So we'll click on the top one. All right, and then this gives me a lot of information about this particular isotope. And so one of the main things I'm interested in is I want to know if it's radioactive or stable. So if it has a half-life, it's radioactive. And in this case, this tells me how long it takes a sample of this isotope to decay. So this has an isotope of 21 minutes. The other thing we're interested in is how does it decay? And so under the decays, sometimes there's a list, sometimes there's just one. In this case, there's just one, and it can decay by electron capture or beta plus. Right? And beta plus is the nomenclature that this app uses for positron emission. And this is not uncommon. Generally, if it can decay by electron capture, it can also decay by positron emission, and we don't necessarily know which one it's going to do ahead of time. So what you can do is you can pick one, either pick electron capture or pick positron emission, and that's how it's going to decay. The other nice thing is it tells us what the daughter is. So when we write the equation, we can check and make sure we get the same thing. So what I'm going to do then for this activity is for each radionuclide, I want to write down the equation for its decay until I get it stable. So for the first one, osmium 180, I'm going to do positron emission. I'm just going to pick positron emission as opposed to electron capture. And so the nuclear equation for that would be this. So osmium 180 does positron emission, and that gives me rhenium 180, and that matches with what the app told me. And then the nice thing here is I can just click on that daughter in the app, and it will take me to its page. And so I can see that the daughter, rhenium-180, is also radioactive. Now it has a half-life of 2.46 minutes, so it's still radioactive. And it is also going to decay by electron capture or positron emission. So I'll write the nuclear reaction for the positron emission of rhenium-180. And when I write the equation, I see that I'm going to get tungsten-180, and that matches with what the app tells me the daughter should be. So let's click on tungsten-180. All right, tungsten-180 is still radioactive, right? It has a half-life of 1.8 times 10 to the 18 years, so that's a pretty long half-life, but it's still radioactive. And its mode of decay is going to be alpha decay. So I'm going to write the alpha equation, or I'm going to write the nuclear equation for the alpha decay of tungsten-180. And when I get the correct nuclear equation, I see that it's going to be hafnium-176, and that matches what the app tells me. So now click on hafnium-176. All right, and at this point, I see that hafnium-176 is stable, so I can stop. So this would be the end of this particular problem. And then you go on and do parts B, C, and D. Then we get to part 2. And so for this one, we want to do the same thing. I want to write out the decay series, but these are going to be longer. And so it could be a little bit tedious to write out the nuclear equation for each one. So we can do a bit of a shorthand. And so I'll show you what I mean by that. So the first thing I'm going to do is look for actinium-225. So the easiest thing is probably go back to the home here. So I'll go home. Now I want actinium-225. So I can do AC 225 and go. And so again, there's just one isotope in the list. If there was more, we just click on the top one. Okay, I can see that it's radioactive, and I can see, right, it gives a couple different decays, but I want the top one. Generally go with the top one. So it's going to be alpha decay, and that's going to alpha decay to francium-221. So what I would write is, in my shorthand, is actinium-225. It's going to be alpha decay. It's going to give me 221 francium. So then click on 221 francium. Still radioactive. It can be alpha decay or beta decay, but alpha is the most likely, so that's what I'll go with. And so the next thing I write is another arrow with an alpha above it, and it's going to make 217 astatine. So we'll click on 217 astatine. Still radioactive. It's going to be alpha decay again, so I'll do another alpha, and this is going to make bismuth-213. So that's what I'd write for that. Now we'll click on bismuth-213. Oh, hit the wrong thing. Try again. Still hitting the wrong thing. Okay, there's bismuth-213. Now, its most likely type of decay is beta minus, and so that's regular beta decay. So I can write, and its daughter is going to be 213 polonium. So bismuth-213, beta decay, polonium-213. Let's check on polonium-213. All right, still radioactive. This is back to an alpha decay. So I'll write alpha decay of polonium-213 will give me lead-209. So we'll check on lead-209. Still radioactive. It's going to be beta decay. So I'll write, I've run out of room. So, this is likely to happen. So I'm just going to start going down now. So lead-209 is going to be beta decay. That's going to make bismuth-209. So we'll check on bismuth-209. Still radioactive. That's going to be alpha decay. So rather than going to keep going down, I'll just start going to the left. And so bismuth-209 is going to decay by alpha decay. It's going to give me, I'm sorry, I wrote this wrong. This should be TL here. And 81 here. And so we'll check on thallium-205. And when I get to thallium 205, I see that it's stable, and so I can stop. And so this is what I would do if my problem was for actinium 225. All right, so I hope this was helpful. If you have any questions, please feel free to send me a text, send me an email, give me a call, and I'll answer whatever questions you have.